Welcome to MEI Modelling with Algorithms. We're on the topic of critical path analysis, and this is video 1.1, constructing an activity network from a precedence table. Now, to introduce this topic, we're going to consider a fairly simple problem. So imagine this: every morning you want to toast 3 pieces of bread under the grill, and your grill has enough room to take 2 pieces of bread at any one time, and each side of bread will take 30 seconds to toast. So the question is, if you want to do this in the quickest time possible, how long will it take? Now, we've got 2 choices here. We've got Amy, who says it will take 2 minutes, and we've got Bethan, who says it will take 1.5 minutes. I'd like you to have a little think about this yourself. Who do you think is correct? Just pause your video and have a think about that. Now, to help us think about this, let's make up some notation. So we've got 3 pieces of bread here. So why don't we call those pieces of bread piece A, piece B, and piece C? And of course, each piece of bread has got 2 sides. So we'll call those side 1 and side 2. Okay, so 1 and 2. And then what we could do, well, let's think about Amy's solution firstly, because that seems like you can see why someone might jump to that conclusion. So I guess what Amy's thinking is you might take piece A and toast it on side 1, and at the same time we could take piece B and toast that on side 1. So in any row here, that can be done simultaneously, and so that will take 30 seconds. After that, you might turn those 2 slices over. So then you do slice A, side 2, slice B, side 2. That takes another 30 seconds. And then after that, you have to toast side C. So you would need C side 1. Obviously, you can't do both sides at the same time, so that's all that will be under the grill at that point. And once that side's done, you'll then do C2, and so we can see we have 4 rows there, each is 30 seconds, so that makes 2 minutes. So that's plausible, I suppose, but I guess it looks as if there's potentially some wastage there, because when you're slicing piece C, some of the time the grill isn't full, so maybe there's a way of reordering what we do so that we can actually do it in less time. So maybe Bethan's right, and if you thought about this carefully enough, you might have come up with this solution. So we might maybe start in the same way. So slice A side 1 and slice B side 1. I mean, I suppose you're always going to start by sticking 2 pieces of bread in, so that's kind of always going to be the way we start. But the clever trick then is to take one of those pieces out at this stage. So you take it out even though it's not yet finished. And so, well, let's say we keep let's keep piece A in. So we'll toast A side 2, but we'll switch the other one for slice C and do that on side 1. And if you think about that, once we've done that, all A is now completely toasted. All we need to do is the side 2 of B and C. So we could do C side 2 and B side 2, for example, at the same time. And that's only 3 rows, 30 seconds each. So that's 1.5 minutes, and that means that Bethan was correct. Now, we didn't really use any sort of algorithm there, but what this does show is that problems of this type are not necessarily going to be easy to do, just by inspection or what have you. I mean, this is a fairly simple example, and we got there, but you could imagine a much more complex, maybe an industrial process where there's all sorts of things going on, some things that need to be done before other things, some things which can happen at the same time as other things, and so on. That getting things done in a way which is going to minimize the total time is not going to be an easy task. And that's where critical path analysis comes into play, and that's going to be the topic that we're going to introduce in this video. So this is just a outline of what critical path analysis is all about. So it allows us to plan and monitor complex projects in order to try to do them as efficiently as possible. In other words, do as quickly as possible. Um, and so that usually what the problem is that we're trying to solve is, given the conditions that we have, what is the shortest amount of time that we can do this in. And our modelling assumption always here is going to be that tasks that don't depend on each other can be done simultaneously. Now, the two things that we're going to be using in our modelling are precedence tables and activity networks. They're both ways of representing the problem that we're modelling. In terms of creating a precedence table, we would list the activities and their durations, how long they take, and then identify which activities depend on others before they can be started. Alright, and the main example we're going to be considering in this video is the stages involved in recording and promoting a CD. And so here you can see the precedence table for this process. So each activity is given a label, A, B, C, D, and so on. And each activity has a duration, a time that it will take from starting to ending. And the thing which is really important then is the preceding activities. So these are activities which must be completed before this activity can take place. Some of these activities, of course, A, B, and C, don't depend on anything else, so they are the things which you could get started on straight away. And an important thing to be aware of is that we only show, and we only need to show actually, the immediate predecessors. So, for example, activity F, packing, the only predecessors which are listed are D and E. But of course, if we look at D and E, they in turn depend on A and B. So really F depends on A, B, D and E, but we don't need to list all of them, because by listing D and E that implies that it also depends on A and B. Now, before we move on and construct the activity network for that big example with CD, we're going to consider a simpler example. Now in this example, we haven't even said what these activities are. We're not going to worry about their durations. We're just going to think about the basic logic of how we can turn a precedence table into a more visual representation using a directed network or graph. Now, there are actually two different ways of doing activity networks. The only type that we're going to be doing is what's called activity on arc. Now, what that means is that we're going to represent this thing using a directed graph, and it's going to be the arcs of that graph which are going to represent these activities. Now, what that means is that the nodes are a little bit more abstract. The nodes are going to be referred to as events, but what that actually means in terms of the reality of what's going on might take a little while to get our heads around. Now, we have to start with a node. We can't have a graph without a node. So the first thing we're going to do is we're going to create a node, and we're going to label each node with a number. This is the first one that we've written down, so that'll be node number 1. And so any activity that can start straight away will start from this node number 1. Now what we can see in our table is that there are two activities, A and B, which can start straight away because they don't depend on anything else. So they start out from node number 1, event number 1. And then we see that activity C depends on activity A. So we need to construct our graph such that that is shown. So what we'll do is we'll create another event here which happens once A is completed. That can be event number 2, and then activity C can start from there. And what that ensures then is that activity C can't happen until activity A has taken place. Likewise, activity D, that depends on activity B, so we need to make sure that that can't start until activity B has taken place. So let's put event 3 here, and we can have activity D leaving off from there. So far so good. We also have activity E, which also depends on B. So what that means actually is that this event number 3, we're going to have two activities starting from there, because there are two activities which depend on the activity which has led into it. So that is D, which we've already got, and activity E. Now this is where we need to start thinking a little bit more carefully, because what we see there is that activity F depends on C and D. So that can only start from a single event. So what that means is that the event that this starts from must be one that both C and D connect into. So these need to come together now, C and D, to a single event, which will be number 4. And activity F, because it has to depend on C and D, must start from event 4, like that. And then finally, activity G depends on E and F, so that means that these two activities must connect to our another event, which will be number 5. And then that activity G depends on both E and F, so that can go there. And then one final event representing the end of the process, which in this case is event number 6. So that's a simple example completed. Make sure that you think carefully about the reasoning that we underwent there in order to create this thing. You'll recognize this. It does look rather like a network representing flow, and indeed we do refer to this start node as a source and this end node as a sink sometimes. So there is a connection there with what's gone before. Okay, so now we're going to turn our attention to the main problem that we're going to look at in this video, which is the production of the CD. Now, we saw that table earlier. It's the same information which is on here. The actual names of the activities are no longer listed, but in terms of creating the activity network itself, they're not so important. We do have the durations this time, and we're going to be writing those durations down as we draw the activity network. So let's go through the process again of how we create the activity network. First thing is that we will make a starting node, a source, and there it is, and that will always be given the number 1. And then any activities that can start straight away can then be added. And notice that those durations are now written in brackets next to the activities. They are in some sense analogous to the weights on arcs that we've seen in previous networks. So before we can go any further than this, we now need to think about the precedence table and what needs to what activities need to have taken place before others. So activity D depends on A, so that means that we need to have an event, a node, at the end of activity A that D can then start from, like that. Okay. Similar for activity E, that depends on activity B, so there must be a node there at the end of activity B. E starts from that, and you can see that these two things have been drawn moving together. Well, that's because we're looking ahead now here, and we see that activity F depends on D and E, so they must join together at this node, and F and G, notice they both depend on D and E, so they must both emerge from the node that we've just included there. And we can see that activity H depends on activity F, and activity I depends on activity G. So there we go. Two events at the end of each of those. H comes after F, and I comes after G, and then we have a final event which depends on H, I, and also this activity C there, so they must all come together at event 7 for this final activity J, which takes us to our sync event, which has been given the number 8. And that's it. So just one thing to comment upon, one thing to point out is, and this is something that actually is a requirement in the, sort of when you're talking about this formally, that each activity can be uniquely identified by an ordered pair of nodes. So activity D here, for example, takes us from node 2 to node 4. So, and there's no other activity that does that. And also with the numbering of the nodes, the second number will always be greater than the first number. So that concludes video 1.1. So we've seen how to construct an activity network from a precedence table. In the next video 1.2, we're going to look at how we sometimes need to use what are called dummies in activity networks.